Hello everyone, welcome to the Deep Learning Retrieval Hands-on session. My name is Zhou Tong and I am a machine learning engineer from LinkedIn. So in this session, we will walk through the steps to build a simple embedding-based retrieval system using an open source tool, elasticsearch. And we will also introduce several algorithms powering the scalable approximate nearest neighbor retrieval using two open-source Python libraries, MMSlib and Faiz. Now, before we go to the content of this session, I want to briefly describe what is a deep learning retrieval system. As you may know that the traditional retrieval systems are based on terms. So a document or a query are usually represented as text sequences or simply a bag of words, so that we can match those documents based on the words that they have, which is also, the words are also called terms. However, a word itself can have several meanings, and so as a sentence. And we want to learn, a better representation of the documents and queries through deep learning models. A good example is that the recent BERT model, which is built on large corpus to learn the generic semantic meaning of words and sequences. So it's based on a supervised learning model that can learn a high dimension representation of those words and sentences. And this also poses another challenge of retrieval, because now all of them are represented as high-dimensional vectors, and the traditional retrieval system will no longer work. And that's why we need a new system, algorithms, and method to build to tackle these retrieval challenges. So the session agenda will be 3 parts. In part 1, we will spend roughly 5 to 10 minutes setting up Elasticsearch. And in part 2, we will build an embedding-based retrieval system on a movie lens dataset. And in part 3, we will introduce several approximate nearest neighbor algorithms, which is kind of the hero behind the system to bring the scalable and faster services. So you can see here is the retrieval flow overview, and it contains 2 parts. On the left is the indexing, and on the right is the retrieving part. So on the left, let's look at the flow. The documents, which is a sequence of texts, are first converted into vectors by some learned embedding models. And then these vectors are indexed through index services so that they can store efficiently and retrieved also efficiently. And on the right-hand side, the retrieval flow will be similar. The query are first converted into vectors for the same embedded model, and then run through the index services to return the retrieved documents. So throughout the session here, for the embedding models, we will use some pre-trained models from Google, which is a universal sentence encoder model. And the index services will be the Elasticsearch. Now let's get started. So in part 1, we will try to set up the Elasticsearch server locally. And here is the link about the tutorial, which you can get full details of how to set up Elasticsearch by going through all the steps. So these steps may contain some part to set up your account, and you can get it for free for like 14 days or 2 weeks. And we will simply avoid doing a bit of registration work with simply 2 steps. So the first step is to download the Elasticsearch archive and set up a local server here with Colab. And then we will create a client connection to the local instance using Python. So as we're trying to download the archive and the data, you can find all of them here on the left side. Because I have already pre-downloaded and installed them, so it all shows up here. But we will quickly run through them to do that again. So download the archive. This is usually pretty fast, depending on your internet connection. And this section is in Python to start our sub-process. So it may take like 30 seconds to like 1 minute. So if you type this part too quickly, you may see something like a failed connection. But as I have already run through that, you will see some server information already set up. So let's take a look. There's some interesting information. So first about this version that we're using, which is 7.8.0. So by far, this may be the latest version that we're using. And there is also a Lucene version because Elasticsearch is based on Lucene, which is another very powerful and popular open source search engine. So once that is done, we will using Python to create the client. So first step is to install Elasticsearch library. Yeah, so I already installed them previously, so it will shows requirement already satisfied. And then you run this part to create the client. Here I also added the link about the API documentation, which includes all the sample code here, plus some other examples of Elasticsearch use cases in Python. And after that is set up, you can confirm that the local server is run properly by checking the client information, which will show the exact same information again as we see previously. So now you can pause here for several minutes to see if you can set up everything correctly. To the second part. So the part 2 will be an end-to-end step to build an embedding-based retrieval system. So as we have seen above in the chart, there are mainly two parts. So one is the indexing and the other is the retrieving. So both of them requires converting documents into vectors for some learned embedding models, and then we'll be index them into the system and retrieve the query for the top scored ones. And so in this example, as I mentioned earlier, we'll use a pre-trained model. So for the sake of time, to save us effort building models. And in this case, we're using the universal sentence encoder model, which is available on TensorFlow Hub. And so that's a good kind of generic model to learn the semantic meanings of sentences and words. And they provide a decent baseline for many NLP tasks. But in practice, it is also necessary to train a deep learning model for your targeted applications for better performances. So here the code in this section is adapted from Elasticsearch's blog, which they first time introduced the text similarity feature with vectors. So for more details, you can click into this part and see the blocks which introducing what is embedding and why they're powerful, and some rationales of why and how they build these features, and there's some sample use case of how to run it through that. So no worry, we will go to each of them in this section with details. So first thing is to download the movie lens data. So movie lens data is kind of very classic data set about movies and users' comments and ratings. So we will simply using the movie's title and genre information themselves to build our system so that we can retrieve the movies based on their titles. So so in this data set, there are roughly 60K movies. And we can see, let's run through them one by one. Yeah, so the downloading data may take several minutes. And once that's ready, you can see them on the left side as well. Okay, let's refresh. Yeah, the data is there. And then unzip the data set. So you can check here or either on the file part here. You can see that it contains multiple data set. And in this example, not sample data, but this one, we'll be using this movie.csv file. And let's try to load data and see what they are. Yeah, you can see that this data is actually very straightforward. There are only 3 columns, and one of them is about the ID, which will be used to find the information of the title and genre. And here, the title also included the year that the movie was released. And there are roughly 60,000 data set. And then we will build an index with the document vectors. So the embedding model will be the pre-trained sentence encoder model. And there are actually more models available from TensorFlow Hub. So let's click into them. And in our example, we actually use the universal sentence encoder large. This is simply because it has the model for TensorFlow 2, which have a cleaner API so that you can avoid all those tokenizing and conversion steps. And here are the Elastic Index APIs. If you're interested, you can take a look. So it will give you more detail of what API is available. And we will be focusing on actually a small set of them. So there are 2 sets of APIs based on either single document or multi-document. So the one we'll be using is index. So that's create an index for your documents. And for efficiency, this is usually done in batch, so that the elasticsearch API provide a function called bulk to do that in batch. So here are some examples of this bulk API operation looks like. And each part in the curly bracket are about one single API operation. So the first one here, so these will be just examples that we will construct in the later cells. So the first part is to create an index. So simply give it an index name and the ID and store the information. So that's do the index. And we can also delete them or update them accordingly by providing the relevant information. So let's see how we can do it. Now, first part is to import relevant libs. And we will also using this timer function to calculate how much time we spend for the indexing and retrieving steps. And here we're trying to load the embedding API from the universal sentence encoder model. Yeah, this may take a bit while as that's a large model, but once that's loaded, inferencing will be pretty fast. And it also supported batch inferencing. So you can see a sample here is the sentences put in a list. So you can add more sentence into that list, and the function will do the batch inference. Okay. Once that's loaded, let's try to run this example. So you can see that here's the dimension of the output. So basically, for this sentence, the model output an embedding of size 512. And given there is only one sentence, so the first dimension is 1. So if you append more sentence here, it will update accordingly for the first shape. And also, let's set up some constants here for the index name, the batch size, the search size, and some mapping information. So because Elasticsearch is taking all documents or queries in the format of JSON, so we need to first provide the mapping information of what the index looks like, what are the fields, and their type of the index documents. So there are also some default setting about the number of replicas and number of shards. And yet remember, Elasticsearch is a distributed search system, so that it will also need information about the shards and other setup. So let's take a look at the property part for this index. As previously we remember, the data contains about a movie ID, its genre, and the titles. So here we can store the title vector in terms of 512 vectors. That is dense vector, and we will also store the movie ID and genres. Okay. So after that, here is just provide some details of the index functions. So this is actually a much simplified version from the log that we showed earlier when they first released the text similarity search. And you can see there are several steps. So this part is we want to create a new index and load the mappings in terms of the JSON format. And then we will do this batch indexing. So we have set the batch size to be roughly 200, meaning that we will handle 200 indexing requests together in this batch. And in each part, we will construct the single request, which contains the operation type, the index name, the ID of the document, and some other informations. So then append it to the list of requests. And once we have roughly the targeted size of requests available, then we will do the index function. So here there is a bug function that we described earlier of how it can do it. But here's some information, detailed information in the Python API that you can check out some other examples. So we will just take the client, the Elasticsearch client that we built first to connect to the instance, and then added the request together to them. So this helper function will automatically do all the requests defined in this list, and we'll just do the quick calculation of how many requests we've been handled, and so here just log the time that needed for building the index. So, and once that's done, it will output information of how many documents we have indexed and how much time it takes. So let's run this function that's created. So here we will actually run the indexing for documents. So remember that this document contains roughly 60,000 documents, which will take quite some time to run. So from this previous run information, we can see that running 2,000 documents takes roughly 100 seconds. So feel free to try it yourself with different document size. And for demo purpose, we will just run this default 2,000, and it will take like 100 seconds. So while it gets indexing, I want to go to the blogs that I introduced earlier when they released this feature. So here it is, which I already opened here. That they also provide some information about their ongoing work and how they plan to do it efficiently. And so feel free to take a look at their GitHub information, and there's a thread discussing the ongoing work about more scalable algorithms that they're building. So here, they also provide a sample script to run for other use cases. So if you click into that, there will be more examples from this GitHub repo. Yeah. Let's go back to see the progress in the indexing part. Yeah. So here, let's also check out the API for the bulk helper. Yeah, so here provide more information, like some examples of how you can create the request and load the data. So feel free to take a look when you have more time. So okay, it's done. Now the index is simply built. So you can try more examples in this API. For example, to get a single document, to update a single document. So there are all info details in this Python document. So the next part is about search with the query vector. And we need to follow the same step of converting the queries into vectors. So for elasticsearch, they provide a function called cosine similarity. And we will use that, and also together with this script score to run and compute the scores between each query vector and the title vector. So because elasticsearch needs a score to be positive, so we append a +1 here. Just make sure the score will be positive. So here is a sample sample script of how we can construct the query. And we here make the query follow a match all sentence, which means we will fetch all the documents by running through this cosine similarity. So here are the other functions. So this function is to return the top movies based on the cosine similarity that's defined. And you can see we first convert the document and convert the query into the query vectors. And because embed function takes the input as a list, so we will format them as a list and convert to a NumPy, because the output here is simply a tensor array. So we'll convert them into NumPy array and into list, and then take the first element. And so here's the formula, the cosine similarity that we just discussed. And here is the script query. So the core function from elasticsearch that you can run this search function using the client by providing the index and also the body part, which includes the search size, meaning how many results we want to return, and then query that's used to formulate the scores needed and the matching criteria. And then source part is what we want to fetch from the documents. We just include the title and genre. So we can use these two fields to see how relevant the document we retrieved are to our input queries. And then this will just outputs more information like the time it takes and also the document details. So you can see this hits terminology. So in retrieval system, we also use this word hits to refer to the documents that has been scanned. Okay, let's run this function. So I prefilled here with a query romance, and feel free to try yours and to see how the result will look like. So by giving this query, I'm expecting something to like related to drama to romantic stories. And if you're running that, you can see the result returned pretty quickly because we're just trying to search within 2,000 documents. And the top one returned actually the true romance. So remember that we are searching using the vectors. So it also performs sort of function in the keywords match where the first result returned actually have the word romance. But this one may not be a good fit because that's a crime or thriller. But the remaining one, you can see some keywords like love, affairs, kissed, and all these related words are kind of related by retrieving using this keywords romance. So they do not have an exact match on the keys, but somewhat relevant. So feel free to try your cases on running through the examples. So I will pause here and let you have a try. Congratulations on successfully completing part 1 and part 2. Now let's get to part 3, where we will introduce the core algorithms behind the scene to power the retrieval. As you may notice that in part 2, when we search with the query vectors, we literally go through each document and calculate their cosine similarity with a query vector and get a score and rank the top K and return. So imagine that this can be really inefficient if you have a corpus of billion or million in size. So that's why we need some scalable way to visit the documents while still having a very good performance. And that's why we need the approximate nearest neighbor algorithms, what we call ANN algorithms. Elasticsearch has also some ongoing work about the algorithm implementation. Feel free to check it here on the discussion and their plan. And in this section, we will go through 3 common algorithms using the open source library nmslib and FAIS. So the reason that we choose these 3 is we have seen all real applications using these 3 algorithms on a large scale. And there are actually more algorithms than these 3, and you can click the link here, which the author did a pretty comprehensive comparison of all other algorithms. Now let's do a very brief description of these algorithms, as some of them can be very hard to explain within a few minutes. So I will highly suggest you to take a look of the algorithms afterwards to get understanding of how it works. The first one is called locality sensitive hashing. So this is a very classical binary hash. Its core is to create multiple hash functions to map vectors into binary codes, so that vectors closely related are expected to hash into the same codes. And now, if you look at the hash function here, so each hash function will convert the vector into a binary result, either 0 or 1. And you apply multiple hash functions to get a binary string. So that's the code we will be using to find similar documents. So the caveat with this approach is that its performance is usually not very good compared to others, but its implementation is very straightforward. The second algorithm is called product quantization with inverted files. So there are 2 concepts here. The first is product quantization, which corresponds to the PQ here. And another part is inverted index, which is the abbreviation IVF. Now, product quantization is actually using k-means as its core quantizer. So what a k-means clustering is actually find a centroid in a large data, and so that each data can be represented using the centroid. And you can see that's a very coarse representation. So what product quantization does is it dramatically increases the number of centroid by dividing each vector into many subvectors and run the quantizer on all these subvectors, so that the number of centroid is increased exponentially. So the reason to do that is once the centroid is known, you can pre-compute all the distance between each centroids, so that at runtime, the distance can simply calculate by check the lookup table and sums up the distance. The second part of this algorithm is the inverted index. So it's actually relies on 2 levels of quantization. The main idea is to approximate a vector into 2 parts, where the first part is a coarse quantizer, where we usually use k-means. And then we apply a fine quantizer on the residuals, which is usually a product quantizer. So in this way, it's more efficient than product quantizer alone when we want to reach documents. The third algorithm is called a hierarchical navigable small word graph. So this method is based on graphs, and what's smart with it is it can allow traversing only a very small part of the graph and get the relevant document. And what it does is actually storing all the graph into the memory, so that all information is available at runtime. And you can see this will have a very high cost in terms of memory. So comparing these three algorithms all together, the first two are kind of functions trying to hash the vectors into some tokens, which we can easily adopt it and integrate it into the traditional search engines, such as term-based search engines. Whereas the third one is building a graph, which is like more independent and more efficient. So please choose them based on your own applications. Now, before we run the sample code, let's see how they are organized here. So here I create several wrapper classes with similar functions and import both Fizz and unzip as their core. So you can see that, for example, these LSH classes, where we will construct using the dimensions of the embedding themselves, and the document for meta information. And the core here is to build the index using this index LSH function and give it a parameter of number of bits. So this is basically the number of binary hash functions that we're going to use. So the larger the number of bits, the less likely that many documents will share a same code. Similarly, here is the IVF-PQ class. So here there are more parameters because we know that there are two levels of quantizations used. There is our coarse quantizer followed by a PQ. And there are parameters like the number of partitions you want to use and the number of subquantizers. So feel free to check the details in this GitHub repo. There will be more examples around that and how these parameters are related. And the third class is the HNSW. So for this index, we're using the unzip, and again, it has some parameters which we will use the most basic one and follow the same format to build the index and do the query. And at last, we will also provide a baseline using the exhaustive search, where we will just basically scan through all the documents, calculate the cosine similarity or L2 distance, and return the top results. So, and later we will show that when we retrieve the top movie using different algorithms, we can compare their result together. Now let's go and start it. So the first is to download the libraries and import them. So I've already done this before. You will see that saying the requirement satisfied. And before we run in all those classes, the first thing is to convert all the documents into embedding, as we did in part 2. The only difference is the format might be different, so we just run here. So remember, the size of the documents is 60K. If you run all of them together with this embed function, it will likely got some out of memory error. So for the sake of time and memory limitation, we will still run the first 2,000 examples. And this may take some time. And again, if that's done, we will run this command to see the shape of embedding. Okay, so there are 2,000 documents. Each of them has 512 dimensions. Let's quickly run these classes. Okay, let's try to run the exhaustive search first. So this will give us the benchmark. And here you can see the top results as well as the search time needed. And so the results are all ranked by the distance. And here is the LSH. Let's run it. You can quickly notify that the result might be very different. And also in terms of distance, here several results share the similar distance. That's simply because they are hashed into the same codes. Similarly, we see in the this result as well. So that's why there is a bit of tuning work to choose the number of bits based on the document size and the data distribution. And we can see from this just tiny example that the search time is actually much shorter, but you can see the performance is not very good. And the second, we will run the product quantization with inverted index. So again, we will see that the result compared to the benchmark, they are somewhat similar, but again, not seeing large overlaps. But some results, like you can see, show up in both results. So this is because we haven't tuned the parameters yet. Remember that product quantization with inverted index has a lot of parameters, and to construct a good index system and algorithm, we'll have to tune that based on the data distribution. So the third one is HNSW. Let's run it again. And you can quickly notice that this result will be very, very similar to the benchmark that we have. Yeah, almost the same, except for only one or two of the results. So that's why this method gained a lot of popularity in terms of its high performance. And for this algorithm, actually, there are some parameters need to tune as well. So here, we just see some examples of the three algorithms and compared with baseline. You can see that all these algorithms actually performs differently. Some may need better tuning, some may need less. And so please choose these algorithms wisely based on your own application. And for more information, you can check here in the reference about different algorithms have been compared. Also the blogs from Elasticsearch when they first released the cosine similarity for text similarity search, and also the data sets itself. So thanks very much for working and running the codes. Please let us know if you have any questions.